Okay, this is Chapter 13, Problem 53, in which we learn how to separate isotopes of uranium. So two isotopes of uranium, the primary ones, are uranium-235 and 238, and they can be separated in a number of ways. In this problem, it's going to be discussed how they can be separated by a gas diffusion process, in which they're combined with fluorine to make the compound UF6. And what we're interested in doing is calculating the ratio of the RMS, or root mean square speeds, of these molecules for two of these isotopes, assuming that they're in gas form and at constant temperature T. And we can use Appendix B for the masses. So here's the pick. It's something like this. I don't know what the arrangement of the molecule looks like, but I'm going to maybe very basically do it like this. F6 combined with uranium-235, so I'll sketch it out like this, versus, and these are supposed to be connected, versus F6 connected to uranium-238. Okay, these two different isotopes of uranium, this one being a little bit bigger, and so this molecule and this molecule will have slightly different masses, and it turns out, even though when they're at the same temperature, they're going to have slightly different speeds. Okay, how can that be? Well, remember, conceptually, we need to figure out what is the relationship between the average speed, or basically the root mean square, RMS, speed of a molecule at a given temperature. So what we need to do is relate kinetic energy, the average kinetic energy, to temperature. What is that relationship? Really, there's one equation for that, which is the average kinetic energy, which is 1/2 m, and the average of the squared speeds. And we write that as RMS squared. That's what we mean by average kinetic energy. That speed that shows up in that formula is the average of the squares of the speed. That is equal to 3/2 times the Boltzmann constant times whatever the temperature is. Okay? So if you have a gas which is in a thermal equilibrium at some temperature, you can relate the mass of those gas particles, the speed of those gas particles on average, to the temperature, which means that at a given temperature, for objects or gas particles that have different masses, they'll have different speeds in order to have this product be constant. Okay, what we want to do is compare the RMS speed of, let's call this one molecule number 1 with 235, to the RMS speed of molecule number 2, which has uranium-238. Okay? What we want is VRMS1 divided by VRMS2. That's what it's asking for, the ratio of the RMS speeds. Okay? So perhaps to do that, why don't we go ahead and, first of all, use this equation to solve for what the RMS speed is in terms of temperature. So taking this equation, solving for RMS, what are we going to do? I'm going to multiply both sides by 2 and divide by m, first of all. So apparently VRMS squared is equal to 3 times Boltzmann's constant divided by the mass, and then I'll take the square root. Okay. When I take the square root, I'm going to write it like this, VRMS, and I'm just going to label this with an index I, so I can be 1 or 2 in this case. It's going to be equal to the square root of 3 kBt divided by m I. In other words, I labels the species. It's either going to refer to species 1 or species 2, and that mass is indicated there. In order to get VRMS1 divided by VRMS2, 1 divided by 2. And if this doesn't convince you that it's worth doing algebra, I don't know what will. We're going to divide this for 1 and that for 2. So let's do that. 3 kBt over m1 divided by square root of 3 kBt over m2. And then look at all the things that are the same in the top and the bottom. With the square root, you've got the 3, the kb, and the t. It's the same up here and the same down there. Those cancel. And likewise, you've got, they cancel. And what you've got then is square root of 1 over m1 divided by the square root of 1 over m2. You've got a fraction in the denominator, which means you basically get to bring that up top and flip it. So convince yourself that this is the same as m2 over m1. If you need convincing, what you can do is multiply the top and the bottom by the square root of m2, and that'll get you there. So this is an important point. You realize that you can figure out what this ratio is without knowing what Boltzmann's constant is, and without even knowing what the temperature is. It's just given by the ratio of these masses. So that's really the last thing to do. M1 is apparently given by, up to small corrections which have to do with binding energy. It's the mass of 6 of these fluorines. So 6 times the mass of fluorine in atomic units. It doesn't matter what units you use. You can use grams or kilograms or AMU. This is 18.998 AMU. I'm going to go ahead and write AMU once, and then I'm going to drop it. Plus the mass of the uranium-235, which comes out to be 235.044. Okay? And likewise for M2, it's going to be 6. It's the same thing. We're using the same type of, same average mass of the fluorine, plus the atomic mass of the uranium-238. 238.051. Okay? And so each of these turn out to be, this is approximately 349 and some change. This comes out to be 352 and some change. When we stick them into this fraction and then take the square root, what you find is this turns out to be 1.004. Does that make sense? Yes, this number is slightly bigger than this number, but you know it's damn close. So hopefully you would have guessed at the ratio of these speeds, since it's somehow connected to the ratio of the masses with a square root, it's going to be close to the number 1, but it's different enough that with a very careful process you can actually separate these two isotopes. So 1.004 is your final answer.